Okay, so today I will demonstrate how you can solve the ROP challenges, return-oriented programming, and ROP 1 and ROP 2 for both 32-bit and 64-bit architecture. And I hope you guys have practiced the DEP3 challenge, which requires you to call 3 functions consecutively. First, call the sum function in the program, and then second, call the what was that? The read function, and then last call printf function to read the flag data and then print out the flag contents in the console. And we will do that kind of the function call arbitrarily in the return-oriented program challenge. So to work with that, please connect to the VMCTF2 server, because that server is like the combined machine for enable the ASRL and then all the other protections, and serving both 64-bit and 32-bit challenges. So after getting there, so if you go to your account and then run fetch week 5, then it will automatically fetch all the directories that is related to the week 5 challenges for week 5. So after getting these directories, we will cover ROP 1 and 2 for today. And then for the next week, we will cover the rest of them. So let's start with the ROP 132. And the README of the file says that we need to call set regid with the GID number 50,000, and then exec ve binsh or some other string with the symlink and 0 and 0. So the important point here is that we need to know how to chain 2 functions using the return-oriented programming, and also we need to learn how to clear all the arguments correctly, and also supply the arguments to the target function correctly to invoke these 2 functions in chain. So we will start with these 2 functions, and then in ROP 2, we need to chain 3 functions, and then in the ROP challenge 4 or something, we need to chain the 10 or more functions to generate the arbitrary string that we can use for the exploit. So we will learn about all sort of things, but today we will just focus on the chaining the arbitrary number of the functions with the arbitrary number of the arguments as the basics of the return-oriented programming. So let's start with the ROP 1, and let's take a look at the source code first. So this is just a simple buffer overflow vulnerability program. So we have an input function here in the main, and then what it does is it print out some of the description and receive our input bigger than the size of the buffer. So there's a buffer overflow vulnerability, but the problem is that, so if we analyze the security status of the program, is that it is enabled with the non-executable. So we cannot inject our shellcode in the stack because the stack is read-only, non-executable. So to check that more thoroughly, so we can check the read-elf output, then it is exec. So the program itself does not apply to with the ASRL, and you can check that information from here too. So it says a non-PIE, so it's not a position independent executable. So some of the code that exists in the program for those addresses, you will have the fixed address. But for the other addresses, for example, stack, heap, and library space, the addresses will be randomized on each execution. So you can see that all such addresses will be changing upon the execution. So that's the setup. And to check that the size of the buffer to overflow, we need to check the read function call in the binary. And then we can know that the buffer is at the EBP minus 88. So let's briefly sketch about the exploit. So we will write an exploit script and import all the phone tools, and then create process ROP 132. Yeah. Then we will start writing an exploit. And we will set a buffer, as we know that the 0x88 is the size of the buffer, fill it up to, let's say, DBP, and then we can fill the save DBP also. After that, we can start writing some of the stack for the calling set regid. We need to call 50,000 and then 50,000 as its argument. And then we also need to call exec v sh 0 and 0. Then calling both of the functions will let us inherit the privilege and then get the shell. And we will do this by reusing all the code inside the program. So the first thing is that we can draw some of the stack diagram. So at the time of the return, we can put the address of the set regid here. Maybe I can put it as this kind of the block. Then currently we don't know what to put here, but we can put 50,000 as the argument of the set regid. So first argument, and then 50,000 again for the second argument. Yeah. So this is the first function call we will make, and then we will put the address of the exec v here, and then put something here, because we will just focus on the calling two functions, so we don't care about the what's about the next. Then we can put the address of the sh string here, and then 0 at here, and 0 at here. And from the slide, you guys might have learned about like if we can return this to pop return instructions, then how it will be executing is like the first, at the return of the info function, it will return to the set regid as the first argument as 50,000, the second argument as 50,000. And then it will do leave return. So it will return to pop return. That means it will pop this value and then pop this value again, then return to exec ve. Then the stack status would be starting from here. Then that it will run the exec v as the first argument as a -8, second argument as a 0, third argument as a 0.2. So it's a first argument of the exec ve, second of the exec ve, and then third of the exec ve. So the important thing is that we need to call this kind of the pop return, pop return, so-called the ROP gadgets, to clear these kind of the arguments values on the stack, and then chain the execution with the new set of the arguments. That's the important part. So let's write the ROP chain. So we call this kind of the step as a one function call as a block of the ROP chain, so we can connect the arbitrary number of these kind of chains to call any kind of function. And then this is why called as a return-oriented programming. So we are actually exploiting the processor's return logic, and then use this kind of the pop gadgets to control the stack and call any kind of function. So it's so conceptually we are writing some of the C program code using this kind of the values and then addresses of the code. So basically we will reuse all the code existing in the program, and we can call any kind of function using this. And to do that, so we've just filled the buffer with all the like the buffer empty space, and then also for the save DBP. So the first thing is like we need to fill the first return address. So we would like to return to the address of the set regid. But the interesting thing is, so for your convenience, I made this function, some function, and then intentionally call the set regid and then execv, these functions in this program. And the reason is, by having these kind of things, we will have an entry, fixed function entry to the binary program. That means, so because this program is a non-PIE, so the code section will not be randomized at all. And then if we get to the GDB and print execBE or print set regid, so we will learn about what this PLT, procedure linkage table, later in not the next week, the week after the next week. Yeah. So we will learn about exploring this kind of part. But at this point, just know this, understand this as like if we use these kind of the library functions in the program, then it will have some of the entry point to such functions. Even if we don't have function body in the program itself, we will have an entry for the library function like this. And if we call this address, then it will internally call the execBE in the library. And also if we call this address, then it will call setRegID function in the library. So we can use these as the symbols for the function. So we can get the address of setRegID from p.elf symbols. setRegID because it has the function entry for that. Then execBE. Then we can get p.elf symbols. Exactly. And we can get the addresses of these things. And then first we need to set the return address as a address of the setRegID. Then we need to find the pop return. So I will just put it as pop return. We will set that later. Right now I will set it as 0. And then we need to put 50,000 for the first argument. And then 50,000 for the second argument. So it's just like filling the return address and then arguments. And then in between the arguments and the return address, we need to put this as a filler for the cleaning up the arguments. So if we have 2 arguments, then we need a pop return. And if we have 3 arguments, then we need a pop return. Then we can clear these 2 arguments, then we can chain the execution to another function. And to do that, the important thing is like we need to know which address of the code contains the pop return, this kind of the gadget. And thankfully, we have a tool called the ROP gadget. And then the usage is like you can attach a -- binary and then binary program name. Then it will output all the available gadgets. And maybe we can store that as a ROP.txt. And then while writing your script, you can, oh no, you can open that as a text file. And then there are some of the sections with lots of pops here. So let me just copy some of that. And do that here. And we need a pop return. And then here's the address of the pop EDI, pop EBP return. So this address, if we return to there, then it will do pop return for us. Then the execution could be something like this. And let's check if this actually calls setRegID and then passes the execution to the execBE or not. To do that, we will use the debugger. And to use the debugger, I will change the file name as a 3223x. Excuse me. Then batch. Then we can set a breakpoint at GDB. Disassemble the input function. So we will break at the end of the input function this address, and then we will set the terminal context. Typo, yeah. And then to do that, I'll change the script as an executable, get into the team-up session, and then I will copy rob 132 to rob 130x. And then I will run this file for debugging. So now debugger can attach it, and I will just continue. So the problem is that my script has ended. So after setting that buffer like this, so they fill the buffer with the 88 and then save the EBP. So our first return address will be set regid, and pop-up return, first argument, second argument. And then this will pop these two, then moves to the execution of the exec VE. We will check that. And to do that, we will send buffer and then to do the debugging. So we need to at least making this script running because if this script ends, then the debugger will be killed too. So we will run that. And now the debugger is attached. Then continue. Then it's stopped at the return of the input function. And it will return to set regid, right? And then at the time of the running set regid. So I just print out like the 12 values of the bytes, from the when we call the set regid. And in the current stack, this is the return address of the set regid. So it will return to pop edi. So if we do it as a x3i, then it will return to pop return, as we set as a return address after the running the set regid. Will be running these instructions. And then the first argument is this one. So this one is actually the 50,000 value as an hexadecimal. And then the second argument is the same. So we just call the set regid 50,000 and 50,000. And then let's set the breakpoint at here, because after running set regid, it will return to this function. So we will set the breakpoint in here and continue. So now it's stopped at the pop return. And now we can see that in our stack, because it has returned, so it has a first and second argument at the stack top. Then this pop will remove this 50,000 from the stack, and there's another 50,000 on the stack. Then second pop will remove that. Then the next instruction is return, and it will return to the exec VE, which we put on the stack. So it will return to exec VE, but currently we did not set any arguments for that. So after that, we can put the return address of the exec VE here, and then arguments at here. Let's do that. So after having this, so we will have 3 arguments. So address of the sum of the string, and then 0, 0. So we would like to run the bin.sh, but maybe we could not find the address of the bin.sh in the program. And in that case, how you can find any kind of the usable string in the program's code is like a break at main, run it, then search for the string main. Then it says at the address of the 80492BA, we can find the address, address of the string main. Excuse me. So copy that address, and then the address string will be this one. And another thing that we need is like after running exec VE, to clear up these 3 arguments, then we can use a 3 pop and return, and we can find that as here, pop return, 3 pops and then return. So we can set it as a pop return, and then the address of the pop return as this address. Then we need to wrap it as a P32. And let's see how this will execute. So focus on the debugger on the right side. I will continue. Then it stopped at the return update function. It will first run set regid. And then this is the return address of the set regid. And then these two are the arguments, 50,000. And then we can break at this address, the return address of the set regid, and then continue. And I will remove the breakpoint. So now it will pop and return. But from the stack, we can see two arguments. So it will pop the first 50,000 and then pop the next 50,000. Now the ESP has the return address as this one. Then this one will call execve. And then this is the return address of the execve. And then this is the first argument, second argument, third argument. And then what's in the first argument? String main. So in the execve, it will execute the main function. Then it says like some of the segmentation fault for now, but we can check that it tried to execute the main as the as the result of the attack. So to check that whether your exploit is correctly run or not, you can do it with the debugger, and then at the same time you can do that with some of the string. So because all the items that we wrote in the buffer is like with the fixed value, so we did not use any kind of the output from the program. So you can write it as the sum of the file. So I will write out the buffer as a file, then run it. Then what I will do is I will do strace rob32, and then put our exploit.txt as the input vector. So this will open the file, this character will open the exploit.txt file and then redirect all the output to as an input up to the program. Then we can see that it will successfully call the set of regid 50,000, 50,000, and then run execve main null null. So the reason why this fails is that we currently have the file named main. So we can copy bin.sh as a name of the main like this. And then what we will do is now we know that our exploit is correct. And we can change it, not touching the debugger. Then we have a p.interactive, run it, and we can get the group ID. Any questions in the RAP1 challenge? So the important part is that so we need to have multiple arguments to call specific function. So 2 arguments for the set regid, and then 3 arguments for the execve. But the important thing is after calling one function, if we can clean up all the arguments from the stack, then the second return will go to the after the value after that the value that we put after the second argument. So it will chain at here and then run this function. And then if we do pop, pop, pop return again, then it will pop, 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 then chain to the next function. That's the 32-bit part of the RAP1. And then let's move to the 64-bit challenge of the RAP. Yeah. So here we have the same type of the program. So non-executable is enabled, so we cannot inject our shellcode, but it has no PIE code and data. So there are some of the fixed region that we can utilize, even if the ASRL is enabled. And then in the program, So if you check the C code, the code itself is the same with the 32-bit one, just the bit width has been changed. So the buffer size, and then like make sure that you need to use P64 for the 64-bit architecture to put some of the values to your stack. Yeah. And then it has the same structure. So we will first check where the buffer is from the disassembly of the input function. Then this is a read call. RDI is the first argument, RSI is the second argument, and then second argument of the read contains the buffer address, and that is coming from LEA RBP minus 80. So we can fill 80 bytes and then 8 more bytes for the saved RBP, and then something else. And in the code, it also has set regid and execve for us, so we will reuse that. So we will write an exploit script. (64-bit). Then first we will prepare a buffer. RBP minus 80 was the buffer, and then so we can also fill the saved DBP, saved RBP, yeah, because it's a 64-bit one. And then we will call set regid. So for this one, we need to call set regid 50,001, 50,001 because the target GID is at that value. Then you can check the GID value from listing the detailed information about this. And then if it says week 5, 50,001 solved, then you need to get the group ID of this one. Then you can check group ID more specifically at here. So 50,001. So the group ID is the 50,001. So we need to get that. So we will call this, and to call that, we need to set up the stack in a different way, because what we need to do is set RDI as a 50,001, then set RSI as a 50,001, and then run set regid. That's the steps that we need to do. So first, we need to return to pop RDI and return. Then put the value 50,001. Then it will run, pop this value to RDI, and then return to the next instruction. So this is how we can chain the execution. So pop to clear some of the data. And then at this time, we need to care about like which register we need to pop, we will pop this value, because the important thing is that we need to set the register value, specific register's value to a specific value to pass the argument arbitrarily. So the finding ROP gadget in 64-bit is a little bit different with the 32-bit one. In 32-bit, our focus is like how many pops were there before we made the return. So we don't care about the register value itself. So we just focus on how many pops there, pop return or pop return, depending on how many arguments we had in the previous function call. But in 64-bit, the important thing is like we need to take care about like which register that we can put the data. Yeah. So we will run the ROP gadget again. So I will put it as a ROP.txt. And then let's open that. And check if whether there's a pop RDI. Yeah. And then we have a pop RDI and return it here. Yeah. So I'll just copy it. So I will prepare the pop RDI and return as a 407E3. Yeah. And then another thing we need to do is pop RSI and return. We need to find that kind of the instruction. Then if we put 50,001, then it will also set the RSI for us. Then let's search about the pop RSI. But there's no pop RSI in return. But instead of that, we can use pop RSI, pop R15, and then return. So basically, we just care about like what's the value in RSI. So we can ignore the value popped to the R15 and then just return. So simply, we don't care about the value in R15. So we have the instruction at here. So we can mark this as a pop RSI and R15, then return. Then the address of that is this. Then what we will do is pop RSI, pop R15, and then return. So this will be the value of the RSI. And then if we put 0, for example, then this will be value of the R15. And then return to the next instruction. So we can put any other instruction address to chain the execution. So after setting the RDI and RSI value as this one, then what we need to run is a set regid. Then it will set RDI as a 50,001, RSI as a 50,001, but as a side effect, it will set the R15 as a 0, but we don't care. And then call set regid. Then it will get the argument values correctly. So how we can fill the stack is, so to the buffer, first we need to put the address of the pop RDI and return. So P64 pop RDI and return. And then we want to set RDI value as a 50,001. And then we will set the RSI and R15 and then return. And then RSI value as a 50,001. And then we don't care about the R15 value, so just put it 0 or 1 or any kind of value that you like. Yeah. And then we need to put the address of the set regid. And then we can get the address of the functions from the p.elf, the symbols, set regid, an address of the execve as p.elf symbols, execve. So by doing this, we can set the RDI, RSI, R15, and then call set regid. And after that, we want to call execve. So let's call execve main 0 and 0. Yeah. So to do that, we need to connect the stack as. So first, we can do pop RDI, then address of main. Then we know that the pop RSI R15 and return. So put 0 and then 0 again. Then it will set RSI as a 0, R15 as a 02. And then maybe we need to have a pop RDX, but here there's a pop RDX. Knob is a null operation, so you can ignore that. And then pop RBP and then return. So we can use this address as a RDX RBP return. So this address is a pop RDX RBP and return. Then put that address at here. RDX RBP return. Then we can set RDX as a 0. Then RBP we can ignore that. RBP as a 0 and then return. Then return to execve. So we will just fill the buffer starting from here. P64 pop RDI return. Then address of a main string, and then pop RSI R15 and return 0 and 0. So set both the RSI and R15 as a 0. Then pop RDX RBP and return. Set RDX as 0, RBP as a 0, and then execve. Then this will call execve RDI as an address of the string main, RSI as a 0, RDX as a 0. Yeah. Then before that, we need to find the address of the main string. So we'll do that. So go to the RUP164 break in main and run it. Then search main, then it will give the address of the main string at here. So we will use that as the address of the main. So right here, this address. Then I will check if this executes correctly with the debugger. So I'll do the same thing. And set the breakpoint at the end of the input function at this address. So I will run the script. So there's a syntax error at the line 60. What is that? So I didn't put the closing parenthesis. My bad. Then run it. So I need to copy RAV164 to RAV16X for the debugging, and then I will run it. So debugger attach it and continue. Oh, my bad. I didn't send the buffer to the program, right? Yeah. So p.send and then p.interactive. So the debugger now stopped at the return of the input function, right? Yeah. And then we'll follow. The next instruction is pop RDI. Yeah. And then at the stack, we have a value C351. So right now, the value of the RDI is 1. But after running pop RDI, then value of the RDI will be 50,001. And then return. Return to where? So pop RSI, right? The gadget that we linked. And then right now we will pop RSI, so it will pop this value. So currently the value of the RSI will be 2, but if we run this instruction, then it will pop this value from the stack. So the RSI value, both RDI and RSI are like a 50,001. Yeah. And then it will pop R15. So R15 will be 0, and then it will return. Return to where? Set regi ID. Yeah. So there are some instructions that the library will do something, and then it will return. And then it returns to the pop RSI R15. So I believe I skipped the pop RDI part in the debugger, but you can see that the RDI is now pointing the address of the main, that as we set up, it will put the address of the main in the first argument part for the execbe before we run it. So pop RDI, pop this value, and then pop RSI, pop the 0 value, and then it will move to pop RDX. So we will pop 02. Then it will return to exec VE. So we got into the exec VE, and then value of the RDI is pointing to the string main. Value of the RSI is 0, and then RDX is 0. So we are actually calling execbe main 0, 0. So now we verify that it works correctly, and we can remove the debugger and change to the real execution. And then we need to copy sh as a main. So we have the file here. And if we run the exploit script, then we can get the shell and get the group ID. So the difference between the 32-bit and 64-bit is that the same thing is like we need to have the way to pop the register value to move the stack forward, and then match the stack to point the return address whenever we have a return instruction. Yeah. So what we need to do is like we need to pop the gadgets like a pop return, something like the sum of the pops and return. And in 32-bit, what we need to care is like only for the number of pops. Yeah. But in 64-bit, because all the arguments are passed by the register, by using the registers, so we need to focus on which register to pop and then match that to supply the value to the RDI, RSI, ILD, RDX correctly. And these are the easier version of the ROP challenge. Then let's move on to the ROP2 challenge. So from the ROP2 challenge, it's something similar to the ROP1, but it has a little bit of application on it. And then the README file says like what we need to do is like we need to open, read, and write. And then we need to supply open the flag file, but we can use any kind of string, for example, main here, and then link the create a symlink from flag to main. Yeah, in that case, even if we open the main file, then the program will open the flag file. And then we need to read from the file descriptor 3 that this open function call will return. So we know that the number is a 3 because number 0 is taken by standard input, and the number 1 is taken by standard output, and number 2 is taken by standard error. So the first file that you will open in the program will have a file descriptor 3 because the operating system uses it sequentially. Yeah. So what we will do is we will read from file descriptor number 3 to a certain size. So we know the flag size. So maybe if we can put size bigger than flag, then it will read the entire flag. So we can put any kind of address here, and then we can write that address, the content that we read from the file to the file descriptor 1, which is standard output. Then we can see the flag content in the console. So basically we will run these 3 functions. And then so in the input function, let's check the source code first, ROP232.c. And then what it does is it has a main function here and then input function. So it says just a write and then buffer overflow here. It's very simple. Yeah. And then to help the calling open, read, and write, it has a function called at here. But if we call this function, it will immediately exit. So it's meaningless, but at least we can reuse these entries because this program has the non-PIE section. So we will reuse open, read, write, and then call those functions. So let's do that. To write an exploit script, import import all, then we will run up to 32. And then what we will do is we will call, maybe we can copy that from you need to call these 3 functions. And then what we need to do is open address of flag, address of the string, then 0, 0, and then we need to put pop return. Then it will do this open call. And then the same thing, read, and then it has 3 arguments, pop return, then 3, and then global variable address, then size. This will invoke the read call, and then same thing, right? It has 3 arguments, pop, 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 return, and then 1, then global variable address, and then size. So we will make these kind of the stacks by using return-oriented program. So basically, we can call any kind of function, supplying any kind of the arguments, and then we can chain them all. So this is the return-oriented programming. And let's check the buffer information. I believe that this will be the same, but yeah. So buffer is at the EBP minus 88. So we can fill the buffer as then the saved EBP. Yeah. And we will construct the function call here. But before that, we need to get the address of the open as a p.elf the symbols. Open address of the read. And address of write, p.elf symbols. And then we need to put the open first, and then address of open, right? And then pop, 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 return. And then to find that, we need to use wrap gadget binary up to 32, and then put it as a wrap.txt. Open the wrap.txt, and then call search for the pop EDI or something. And we have lots of pop and return instructions around here. And let's have it as some of the comments like this, and then pop, pop. We need pop, pop, pop return as the, where is it? Pop, pop, pop return here, right? So we can use this address as a pop, pop, pop return. And then we need to put the address of the string and then address of 0 and 0. Yeah. So the address of the string will be, we will use the main as a string. 0. And it will call open main 0, 0, but it will do pop, pop, pop return. So pop, pop, pop. So it will clear the thing. Then we can chain the execution. And before that, let's get the address of the main. Break a main and run it. Then print, no, search main. And we can get the address of the main here. So we just called open main 0, 0. So open the file name main as a read only. And then we will call read function. Then read function is a 3 arguments too. So we will call pop, pop, pop return to link this chain to the next call, right? And then we will put the first argument of the buffer, that was 3 as a file descriptor, then global address, and then size as a, like the just put 100 because the flag size is less than 100 bytes. Yeah. But the problem here is that where to write, and then we need to have some of the fixed address as a global variable. And fortunately, the binary is the non-PIE. That means, so just to break a main and run it, and then if you run the VM map, then it shows that there's a read and writable section around this address. So because the binary programs the code and data, these are fixed in the PIE. So all the other addresses, there will be the random, but these 3 part, code, read-only data, and the read-writable data, these will be fixed. And then to safely use this area, so if we add like around the 800 here, yeah. So I just changed the last this 0 to 8. And then if you print out some of the values here, and these are all 0, so you can actually put the some of the flag file at here and then read that. So to do that, so address global is this one, and then it will call read from the file descriptor 3 to this address, global variable, and then 100 bytes. And then finally, we will call p32 addr write, and then write has a 3 system call, pop, 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 return, and then file descriptor 1, global variable address, and then size. And then we want to send this buffer to the the program, and then program will react. So we will run Python interactive. Yeah. So if I run it, then you can check with the debugger that how it is actually running, and then you can see that it will do run open with these 3 arguments, and then pop, 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 return to read with these 3 arguments, and then pop, 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 and then write these 3 arguments and pop, 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 and continue to run the program. Yeah. And then this is the how you can chain the all the ROP gadgets and then the return. So this entire the buffer is called as a building a ROP chain. Yeah. So after building this kind of chain, so now it's our turn to test it if it works correctly or not. So not to leak the flag, I will put a fake flag as a main file. This is a fake flag, ha ha ha, something like this. Yeah. Then I will run the exploit script. Maybe I made a mistake. So ex.py 66. So we don't have size. So just put the size as a 100. Yeah, that's my mistake. So now it run the ROP chain and then read the flag file, which is main right now, and then it will print out the flag file in the console. So even if this does not get a shell for you, but at least you can use open read and write to leak this flag file. So it's just an application of the chaining 3 functions. And we just practiced chaining 2 functions in the ROP1, and then ROP2 is about chaining 3 functions. Yeah. And then let's quickly go over to the ROP2 64.2, and then basically we need to do the same thing. Yeah. And then the difference is that the arguments need to be passed by the through the registers, not the stack. So ROP2 64, and then what we need to do is calling these 3 functions. And then we can get the addresses of the functions from the ELF symbols. Read, write, read, write. And then another thing we need to do is that we need to run a ROP gadget. Then I'll put it as a ROP.txt. You can find lots of pops here. So we will copy all these popping instructions and then put it as a comments. And then we need a pop RDI return. Then pop RDI return is this one, 400743. Then we need a pop RSI return, but we don't have a pop RSI return, but instead we have a pop RSI R15 return. R15 return is here. And then we need pop rdx return. And then here it is, pop rdx and then return. Then we will use these three as a gadget. Then we need to set up. We will do. So I will just check the buffer length, and then buffer is at the coming from RSI comes from RAX, so it's at the RBP minus 0x80. And then another thing is like I will just run and then search for the main string, and then the string of the main is here. Address of main is at here, and then buffer is at EBP minus 0x80, and then we need to put the save DBP for it. And then next we will call open main 0, 0. And to do that, we will set the first argument first, pop RDI return. So we need to do pop RDI return first, and then set the RDI as the address of the main. Then P64 pop RSI R15 return. Then RSI, we set it as a 0. And then for R15, we don't care, so set it as a 0. And then P64 pop RDX return. And we need to set it as a 02. Then we set the RDI as a main, RSI as a 0, RDX as a 0, and then we call open function. So we will do the same thing for the read 3 global size, then write 1 global size. Then to get the global variable address, so get back to the GDB again, break at main, run vmmap. Then you can see that these addresses are read writable and they're not changing. And then this address plus 8, yeah, 100, like this, yeah. And then to check whether that's safe or not, you can actually examine some of the values. If they are all 0, then you can use that. So copy this address. So the address global is this one. So we will put P64 pop RDI return, then set RDI as 3 first as the first argument. Then P64 pop RSI R15 return. So we need to put the global address as the second argument, but we don't care about the R15, so we can put 0. And then P64 pop RDX and return to set the third argument. And then the size is 100. And then finally, we can call read function. And then we can do the same thing. So maybe we can copy all these things. But the change to the part is like that we want to set the RDI as a 1, RSI as the address global, RDX is the 100, and then call write. So now we can see that the pop RDI return will consume these two, pop RSI R15 return will consume these 3, pop RDX and return will consume these 2, and then finally call the function. Set the register values and call the function. Set the register values and call the function. This is how ROP chain is chained together in 64-bit. And then we will send that to the program and then wait for the output. Make it as an executable. And also we will create a fake flag. So I will just create a fake flag and then run it. Then it will print out the fake flag. So if you change the symlink to this main file as the symlink of the flag, then you can get the real flag. So today in the tutorial, we learned about like how we can chain multiple functions with the arbitrary number of the arguments in both 32-bit and 64-bit. And important thing is like we need to find the ROP gadgets that has some of the pop, 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 and return. And by using that, we can clear the stack and then chain the call in 32-bit. And also in 64-bit, we can set the argument values directly to the registers by using the pop instructions. But for the some of the pops, we have a pop and return, pop RDI and return. So that's all okay. But for some other instructions, we have a pop RSI and R15 and return. And in that case, we can ignore the R15 because it doesn't matter about that. Yeah. So this is the summary of the what we learned in today. And is there any question?
Actually, Professor, I have a question because
yes,
what a coincidence because I got stuck for a long time in ASLR. So
yes,
I'm reading the article of ROP. So actually, I tried ROP on every ASLR, the challenges. But
yes.
I realized that most of ROP used a combination of open, read, and write.
Yes.
So I also remember that Professor told us this is entrance because you write down the blank the function in the code. Yeah, but except ASLR challenge 3, the other thing doesn't have a write function.
Yes.
So in the case, can we use that write even though we don't?
So if you don't know about the write function address, then you cannot use it. But if you can leak the address of the read, for example, so suppose like the program has the function of the read, then if we call that, then the actual address. So the read function is not in our program. So that is actually in the library space, and then there will be only the entry for the read will be existing in the program. So because it has an entry, so we can call read from this entry, but then not the write function. But the interesting thing is that the write function is already existing in the library. So if we know the address, we can call it. But the problem is that we don't know about the address. But in such a case, we can read. So whenever we call the read function in the entry point of in the program automatically find there is a part of the code in the program that it finds where the actual read function in the library is, and then put the address of that into some of the global area. And if you can leak the address of the read, then using the relative offset that we learned in the ASLR challenges. So if we can get the offset of the read and then write function, then we can get, after obtaining the read function address, then we can calculate where the write function is. So you might need an additional step to leaking the address of the read function to figure out where is the write function, or you can even search for where the exact VE or system functions are. Yeah.
Oh, I got it. Thank you.
Yes. So like this challenge is not enabled with the full ASLR. So like you can reuse all the things in the code itself. But your problem was like what if like your code does not contain read, write, or those functions, right? Yeah. But the thing is like the program will at least use one of the library function. If that is the case, then after calling that function, you can read where the function is located in the library, leak that, and then you can calculate all the library space function address. And then we will actually practice that in the coming challenges in week 5. Any other questions?
If anyone doesn't have any question, can I have one more question?
Okay.
Yeah, because I'm not used to get the value of the filling A. What I mean is the professor usually the full A by OX88 or OX80. Yeah, but in my case, I'm not get used to read the code. So when I usually use the Python-C and print input the value in a GDB. So actually,
Yes.
add more. I try to find out when it crash, I can see the breakpoint, because if the A is 40, 41, 41, 40, 41, that means it's a sign of some location in the A.
Yes.
But I don't think that it's the the solution to get a right position to put in my shellcode. But I try to. But in this week I'm really confused that because when especially for in ASLR 4, when I put the something, it did not get returned what I intend to. What I mean is
so ASLR4 is not about using your shellcode. So that challenge is intended for like calling the system function. Yeah. And then to call the system function, you might curious about like the which address you use for the string, right? So when you try to call, like, for example, system main or something like this, yeah, then you might curious about like where this main function is located. Yeah, a main string is located. Yeah. So if you can find that as any kind of fixed address, then you can use that. Or like if you cannot find that as if you cannot find in any kind of fixed address, then at least you will have the address of the system, right? And then if you can find any kind of string in relation to the address of the system relative to the address of the system with the fixed offset, and then if you can find any kind of string starting with the @ or other sign, yeah, then you can use that as a string value. And then like for that challenge, like if you try to use your shellcode, then it might be a little bit difficult. Yeah. So please solve that with the calling the printf from the printf function, calculate the distance to the system function, and then call that.
Oh, okay. Yeah, I got
Yes.
it.
Yes. Right. Is there no more question? So the due date of these challenges are on like 2 weeks later. So please take enough time for solving these, and then maybe you can feel it like ROB challenges will be much more easier than like some of the ASRL challenges, because like for those challenges you need to interact with the program to get the address, and then like if you couldn't calculate the offset correctly, then the addresses keep changing, so that could cause a little bit of confusion. But in the ROB challenges, most of the things are deterministic. So you can play with the some fixed addresses or something, yeah, to call the function. And then it's more about like controlling the stack, how it is popping the values and then running the program. Yeah. And then like this will be give you much fun than like the ASRL challenges. And feel free to leave any questions to the Discord, and I will post this session as a video too. So yeah, please stay tuned on the website, course website, and the Discord. And thank you for your attention. And let's finish today's session.